Okay, so to start off, I've got four images for you. So let's have a look at them. So 1, 2, 3, 4. Now, quick question. What do all of them have in common? Well, I would be really surprised if you guessed this one here.
Well, they're full of lines.
Huh?
They're full of lines.
They're full of lines, and they're in a circle and these sort of things. But they're actually pictures of times tables. Ah, okay. Pictures of times tables. I better explain this, all right? So to get these pictures, what you do is you start with a circle, and then you pick a random number, okay? And we'll just choose something nice to start with, a 10, okay? So then with 10, we put 10 points on the perimeter here, equally spaced, and then we label them with 1, 2, 3, 4, 5, 6, 7. Okay, let's just go. Actually, we start with 0. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then 10 we also want. So we kind of put that right there again. So that's also 10, that's also 11, 12, 13, 14, 15, and so on. Okay? And then again, and so on. Right? So this guy here stands for 1, 11, 21, 31, and so on. Okay? And now we're going to do the 2 times table. Okay? So 2 times table. And we'll start with 0. So 2 times 0 is?
0.
So 0 is the same thing, so we don't do anything. Okay, 2 times 1 is?
2.
2. Okay, so we connect the 1 to the 2. Then 2 times 2 is?
4.
Okay, so we do this and we keep on going. Pretty obvious. Now 5. 2 times 5 is?
10.
10. 10, remember? 10 is also over there, so we connect that guy up. And then 2 times 6 is 12, which is also the 2. So we connect that one, and you kind of just keep on going like this. Okay? And then you're at 9, and you've pretty much gone all the way around. Now you could go on. So for example, we could now do 2 times 10, and 2 times 11, and 2 times 12, and draw in those connections. But actually, the connections are going to be exactly the ones that we've already drawn. So we can actually stop here. Just to illustrate, let's just go up to 2. 2 times 12 is?
24.
24, which corresponds to the 4, and that connection's already there, right? Yeah. And 2 times 13 is?
36.
Not quite.
2 times, sorry, what?
2 times 13.
2 times 13, 26.
26, and we've already got the 6. Of course, we made a choice there at the beginning, that 10, right? If you change that 10 to anything else, well, the picture changes, but pretty much everything I said stays the same, okay? So for example, if we switch from 10 to 11, we get this guy here, you know, and then 12, 13, 14, 15, and let's just see what happens.
So,
pretty nice.
Quick question.
Yeah.
All these pictures that you're showing, it seems that they are symmetric.
Yep.
In the horizontal axis. Like
that's right.
mirror.
Yep.
Is that for a particular reason?
Yep, there's a reason, and actually let's just give this as homework for our guys here to figure out. So in the comments, tell us why there's a symmetry. Of course, what's much more interesting here is that curve that somehow magically materializes when you kind of up the number that you choose at the beginning. Okay, and actually I'll just highlight it a bit. So there's this strange curve here. It's actually got a name. It pops up all over mathematics. It's called a cardioid. Like in cardiology, it means heart. Okay, so it's like a heart curve, mathematical heart curve. And it comes up in all kinds of places, and I'll just show you a few. Okay, so for example, you can have it as a rolling curve. You roll one circle around another circle, and just see what happens to one of the points on the boundary of the rolling circle. Okay, so for example here. And what it does is it traces the cardioid, okay? Now, where else can you see it? Well, sometimes you can see it in your coffee cup. If you've got a conical coffee cup like this, and the sun is in the direction of one of those green lines in the coffee cup, then you can also see a cardioid in there. Where else? Well, there, right there, in the Mandelbrot set. So the biggest bulb in the Mandelbrot set is a cardioid. The second one is actually a perfect circle. Now, this would be a good one to figure out why is this guy a cardioid? And so just to kind of trace this down somewhere. Now, just for those people who know something about this stuff, that's the equation that we use to make up the Mandelbrot set, and there's a 2 in there, okay? So that's important. We just had the 2 times table, so let's just keep going, okay? Now, yep.
If you want, one more thing about the cardioid shape is that actually as a video producer, I know that microphones, there is a category of microphones called cardioid microphones, and that's because they pick up the sound in that area, from that direction.
Okay, right. Well, maybe we'll do another video on this.
Yeah.
Okay, now we can also, instead of doing the 2 times table, we can do the 3 times table. And if we do the 3 times table, well, what we get is this pattern here for initial choice 10, and then I'll just, up the numbers there. And what do we get? Woo, another curve. Another very famous curve. This is called the nephroid, which is kidney, Okay, whereas this one also has a rolling curve. Here the circle that rolls is half the size of the one that is rolling around. It's also in a generalized Mandelbrot set. So remember, before we had an exponent 2 here, now we're talking about 3 times table, we change the exponent to 3, and you actually get the main bulb here being the nephroid. Okay, we also get it in a coffee cup. This time we need a straight coffee cup, and the light rays kind of come in like from one side, okay? So they kind of come in straight like this, and then they kind of bounce around inside the cup and make up this curve. Actually, this way of making up a curve is called a catacaustic in mathematics. So there we go. What else have we got? 4 times. You can kind of see a pattern now. 4 times gets you three petals. Before we had 3 times 2 petals. Okay, and then all these other things that we've kind of been highlighting here, they work too. There, exponents gone up to 4. There's the generalized Mandelbrot set here. We've got the rolling curve happening again, right? And then just for good measure, just one more guy here. That's the 5. So it gets 4 petals. And we've got the Mandelbrot set here, and we've got the rolling curve. So all very, very neat, okay?
So the number of petals is n-1.
Yeah, it's n-1. And it keeps on going like this. So there's a pattern like this. Okay, so let's just start again with 2. Okay, so that was 2 times table. Now, one really nice thing to try is actually make the increments not 1 to 3 to 4 to 5, but actually do smaller increments. Okay, or actually do the transition here continuously. So I'll just show you, if I just do the multiplication times 2.1, what you get? 2.1, 2.2, 2.3, 2.4, 2.5, 2.6, 2.7, 2.8, 2.9, and 3. And you can kind of see how the cardioid turns into this nephroid, which is kind of cool, right? And now I just let it go, and the numbers are going up, and you can see the petals going more and more and more and more, right? So this continuously. And well, you think, well, that's probably what it's going to be. You can also look at this in the Mandelbrot set, and you can actually see exactly this sort of pattern here happening in the middle. And if you kind of push the exponent to infinity, the whole thing kind of turns into one big circle. That's pretty cool. Okay, and that's, I think that's the end of it. But no. Let's just keep going here, right? So the petals are pretty much going to go away now. But if you just look at what's happening here, you see there's a lot more, structure somehow being hinted at, right? I mean, we're moving very fast at the moment, right? We're moving very fast. But if you actually went through this frame by frame, you would see a lot of really, really nice structure happening. And I've highlighted a bit here. So just a few of the frames that you get, some really amazing stuff happening here. So if you stop at 33, you get this one here. Stop at 34, you get that one here. And there's a couple of other highlights here. There's a lot more. It's just this is how many I could fit here, right? Okay, and maybe have a close look at some of them, okay? So here we've got 4. Now the number that all these correspond to is actually 200, okay? 200. What we're really doing here has a special name in mathematics, okay? So what we're really doing here is we're doing the times table modulo 200, okay? So it's got a special name. It's actually incredibly important in all sorts of applications to do this sort of modular arithmetic. Okay, but anyway, for our purposes, you understand how it's built up, and if you know a little bit more, you know a little bit more. Okay, so for 2 times table, we get the cardioid. For the 34 times table, modulo 200, we get this guy here. And then some other things, interesting things happen. So for example, if you multiply by 51, we get this guy here. And if you multiply by 99, we'd get that guy here. And obviously, I mean, if you just look at the 2 numbers here below, 51 is pretty close to, 1/4 of 200, so must have something to do with that. 99 is pretty close to 1/2 of 200, must have something to do with that, right? Okay, now, I really wanted to explain something. I really want to explain where this one here comes from. And well, I mean, the first time I saw this, I was pretty surprised, like pretty much everybody sees it. But then I remembered something. I had seen the cardioid before in, many, many different guises. And in one particular one that I was familiar with, I could see where the connection is. And I just want to tell you about that one, okay? And it's got to do with this light rays bouncing around. It's a little bit different from what we had before, okay? So basically we've got a circle here, and then we've got a light source right over on that side, right? And that circle kind of reflects the light, right? So we switch on the light over there, and then, well, what happens? Well, light rays kind of emanate in all kinds of directions, get reflected off the circle, right? Bounce around, and you kind of see this pattern here emerging, the cardioid. Yeah? So I knew this one. I had actually calculated the curve, from this description at some point at university, okay? Then they can actually really see very easily why the cardioid comes up in the 2 times table. And I just want to show you, okay? So let's just highlight like one of those rays coming out. It kind of hits the wall here, okay? And then it gets reflected at the same angle as it comes in, right? So this angle here that you see here is the same as there, right? And you can see it kind of goes like that. Okay, so what does that tell us now? Well, if we kind of put this line here in the middle, it means that this side really flips over to that side here, which means that this segment here in particular is exactly as long as that one here, right? So if I travel from this light bulb to this point, and then from this point to that point, it's exactly the same distance, okay? So that's going to be important. Okay, so let's make this 0. Let's call this n. So what's 2n then, right? So to get 2n, what you have to do is we have to measure this distance here, and then we have to measure it again. Where do we get? Right up there. Right? And so it's pretty clear that when you do the 2 times thing, you get that reflected ray, in the picture. Just to finish off, I'm going to show you a little bit of a movie of all this stuff evolving a little bit slower than what we had before.